He asked me yesterday if I'd come and stand in for him. I was meant to be here as a delegate, so it wasn't a big issue for me to come down. So welcome to the Rutherford Appleton Laboratory site. Welcome to Diamond. Most of the people in here I know, so apologies, you're maybe going to hear a lot of stuff from me that you've already heard before, but there's two other people here I've met before, Adelaide and Dominic. Thanks for coming as well. Everybody else apart from those two guys is from the Low-Rise Consortium, which is one of the NERC-rate consortia, and so we have representatives here from Hydroframe, I think, Dominic, yes, and then from Tree. So we have the full spectrum of the rate consortia represented here today. And what we're essentially trying to do today is to help the different rate consortia learn about what is possible to be done down here at the RAL site, the range of different facilities that we have here, and to see if we can do some of rates science at these facilities. The first thing I actually want to do is to try and get a show of hands from people with regards to the tours that they would like to go on this afternoon, because that's going to help the facility scientists and myself plan where we have to have people and when we have to have them there. So I'm going to start off with Diamond. So if we could have a show of hands of people that would like to go see Diamond. So we've got most of Low-Rise and we've got Tree. Who would be interested in seeing the Manchester X-ray imaging facility? So that's X-ray tomography. So we've got Dominic and we've got quite a lot of Low-Rise folks. Central Lasers facility. So we've got 3 people, 4 people from Low-Rise. Yeah, if people hear a presentation go, oh wow, I want to go see that, that's fine, but it's just to give us an idea. So for the Low-Rise people, I think that's going to be the ones that most want to do 2 things at least, so we can try and organise that over lunch. And then Neutron. We've got 1, 2, 3, so that's Low-Rise. So I think we've got, okay. We're a little bit bound by time, I think, Steve, in terms of when we can do tours with you because of a meeting that's happening.
That partly depends on numbers, so by the look of it, I don't think that's going to be too much of a...
Okay. Okay. So I think...
How many diamond hands were up?
There was about 10 diamond hands up.
10 is my limit.
Okay. I think we'll be all right. Okay, we'll come up with some sort of schedule over the lunch break, and we'll let people know what's happening after lunch. In terms of other things that's happening today, I'm going to give you a quick introduction to what the Environmental Radioactivity Network is. Then we're going to hand over to facility scientists, and so Fred's going to give us a talk about what's possible to do at Diamond. We'll have Rutherford talking about ISIS and neutron imaging. Andy very kindly came along and he's going to give us a talk about things possible at the Central Lasers facility. And then finally after lunch, Peter Lee's going to come down from Mixif to give us a talk about the various things that we can do up there. We have a discussion and question answering session in the timetable, but I'm not quite sure if we're going to need that, because we could have questions after each talk and we'll of course be able to discuss things over lunch. So we might try and move the tours upwards towards 2 o'clock, and then that means that everybody can get back home a little bit earlier. So I know that would certainly help me with my train situation as well. So very quickly, I just want to highlight to some of you that might know about what the Environmental Radioactivity Network is and what it tries to do. So it's a network that's run by Sam Shaw and myself, and we have Oliver here, I think. There he is there. So he's the network administrator. We're funded through something called the STFC Futures Programme, which is a scheme where they're trying to ensure technology and skills development in a range of what they call key global challenges. And one of those key global challenges that they're interested in is radioactive waste management and the behaviour of radioactivity in the environment. And so Sam and I set a network up in the Futures Call to address problems in that area. And so the key aims of the Environmental Radioactivity Network is to try and improve communication between the researchers that are working in this kind of broad field of environmental radioactivity and then scientists here at the RAL site and elsewhere in the STFC portfolio, trying to share knowledge and expertise across the entire environmental radioactivity research community, try and better our experimental techniques and transfer that knowledge between teams, and also models, computer modelling, and general scientific insights. And then finally, one of our remits was also to try and help create new multidisciplinary project teams. And so that's something that we've been involved in actually with RATE from the inception of the RATE programme with NERC. In terms of the facilities that we work with within the network, we work with Diamond, so synchrotron-based techniques. We work with ISIS for neutron techniques, and then Central Lasers facilities. So those are the three places that we can go and see today. Also, more laterally, we've started to work with MIXIF, so the Manchester X-ray imaging facility that's based down here with a collaboration with Diamond. We also have a range of things that we're doing in terms of scientific computing, and that might be interesting for some of you that are here today. We're not specifically dealing with that today, but we do have ties in with the guys based up at Daresbury. We are running a training school in the new year on scientific computing, so if that's something you're interested in, come and either speak to myself or Oliver today, and we can give you a little bit more information on that. And then finally, I just want to talk specifically to the reason why we're here today, and that is the NERC RATE programme. So STFC and NERC decided to wed ourselves together in terms of the RATE programme. So the two STFC Global Challenge networks that have anything to do with radioactivity, so ourselves and the Geological Repository Network, came into the RATE programme on the proviso that we could provide some training and funding to those things. So in terms of what we can actually offer the RATE consortia, we can offer training courses, and we've already done some activities here for PhDs and PDRAs there. We're also quite happy to train any PIs as well that are interested in learning about techniques hosted at the STFC facilities. We can also fund international travel and provide help with subsistence as well. If you are doing similar science, so synchrotron science, neutron science, laser science, or computer science in other countries, and the only proviso there is that you provide feedback on what you've actually done in those countries when you return from doing that, and we'll be able to help pay for flights and hotels and things like that. And also we can provide funds to allow people working in the RATE consortia to come and actually meet with scientists down here at RAL. So we can fund mentorship schemes there, or just simply meetings to come down and plan experimentation. In terms of getting access to those funds, quite simply, all you've got to do is visit our website, and if you visit our website, we have a number of forms that you can fill out online telling us what you want to do and how much money you need to do it, and we usually turn around acceptance on those proposals very quickly. Also, if you want to have a more general chat about possible things that we can help support, you can either contact me, Sam, or Oliver via email, and we can engage in conversation about things to do there. So with that, I'm just now going to hand over to Fred, who's going to give us our first talk today, and that's our introduction to techniques that we can use at Diamond. Thanks, Fred. I'm going to give you...
Thanks, Gareth. So, yeah, the first thing I learnt today was never put a diamond pen in your pocket. But apart from that, so I'm going to briefly talk about access here, because it's, for those of you who haven't used synchrotron before, synchrotrons are things you have to plan reasonably well for, so even in a 3 to 4 year project, you sort of have to plan quite a long time in advance of any experiments you want to do. Then I'm going to go through, but because of having looked at the forms that Sam and Oliver provided in terms of the interest, these seem to be the principal synchrotron techniques that people said they were interested in, so those are the ones I'm going to talk about, and I'm just going to talk, well, very almost a little bit about the beamlines, but more about some of the work that's been done there. So a little bit on some of the XF's work that's been done on uranium on B18, some work on the microfocus and nanofocus lines, so that's I18 and I08. I mean, the examples I picked for nanofocus and microfocus aren't necessary. Well, I picked some examples from I18 that aren't radioactive, and then some radioactive from other synchrotrons, because the I08 scanning X-ray microscope only opened in July this year, had its first user, so I don't have any data from that to present, though I know that there was a very successful ion experiment by Liana Benning, so it does have relevance to certainly some of the sorts of things some of you might be looking at. And then I'm going to talk very briefly about I12. I'm just going to show one tomography example of a fossil, really, because I'm pretty sure Peter's going to be covering I13 and tomography in his talk this afternoon, so I'm not really going to show hard X-ray tomography, because the difference between hard X-ray tomography and sort of the I13 tomography is only really size of the object and the energy of the X-rays, so those are sort of, so by showing one example, hopefully you see what I12 can do, and I'm sure Peter's going to tell you what I13 can do. And so access. So access here is mainly via peer review panel system, which the deadlines for are the 1st of April and the 1st of October every year, and that's for beam time 6 months on. So we have a long lead time for any experiment. Effectively can be nearly up to a year. And average oversubscription rates at Diamond currently are about 2 to 1, but that obviously does vary beamline by beamline. There is, for people with grants like yourselves, possible long-term access, which does make the certainty you're going to get beam time a bit higher, and that's, you can write a 2-year program. Generally, you'll have to have done at least one experiment to prove it works for the panel to give you long-term access, because I don't really want to give you 2-year access and find that actually your experiments don't work very well after a year, and so they've given away. So they'd rather you did an experiment first, probably on, that's just my experience. And if you only got a few XF samples to model, and they're reasonably straightforward, so that doesn't mean radioactive, then there is a rapid access route on B18 where you can submit up to 6 samples, and they'll measure them within 2 to 3 months at any point, basically, normally, as long as there's a good scientific case behind them. So if you've got just a few standards you forgot to measure or something, that's best, well, as long as they're not radioactive again. So that's Diamond from the top, and these are the beamlines I'm going to talk about, hopefully. Yep. So I'm going to talk about I08, I12, and the spectroscopy beamlines, which are 18, 20, and 18 again. And that's this is Diamond House, where we're about here at the moment. So luckily the spectroscopy buildings are quite useful because they're easy to get to, except for I08. On the tours this afternoon, I intend to go to this I08 and the spectroscopy beamlines. So if anybody desperately wants to go to Jeep, I can ask about going to Jeep as well. So I just thought I'd mention before I talk about the beamlines, our policy with radionuclides. In that, 2 things really determine our policy for radionuclides. One is hazard and the risk of contaminating beamline. So that's our bottom line, is we never want to contaminate a beamline, and obviously we have to be safe in the fact that whatever you bring here is safe. So we have lowish limits for XAS and for anything but uranium technetium. At the moment, actually, we're trying to put together a project to make those limits a little bit higher, and also introducing a sort of high activity handling lab, but that's a sort of 2.5-year project, so that sort of will outrun most of rate to some extent. Samples need to be either solids or solutions, but not powders at the moment. They have to be in some sort of containment, and there is a small radiochemical lab available for some sample use out of office, and there's a guide that tells you more about all this on that website. I assume you might want these talks on your website at the end of the day. So, XAFs at Diamonds. There are 2 scanning beamlines at the moment, B18 and I20, though I20 is in a little bit of a state of flux at the moment. B18 does fast scanning, can do elements from phosphorus upwards and down in a mineral environment to somewhere in the low hundreds of ppms. In a biological environment, it can go a lot lower, but mineral environments are more absorbing of X-rays, so you tend not to be able to get quite as low. probably down into sort of high tens of ppms for in an organic type environment. I-20 will do more dilute samples, can also do high resolution spectroscopy, so that gives you high resolution zones, which for instance is better at picking out uranium oxidation states than say, and it can do elements from titanium upwards in the periodic table. And just as a very brief reminder of what XAS is, so that's the absorption. We scan the energy and we look at the absorption of the sample. This is an example from Adrian Finch of how Zanes in magnesium compounds change, and look at when he was doing some fossil work. This is nickel in a manganese oxide environment in a laterite ore. It can be done in situ down to about a few ppm on I-20, they're a bit higher on B18, and it gives you the local atomic environment electronic structure. So this is a study by the group of Rizlan Bernia Latmani done on B18, where she was looking at how uranium, which was coming from a mining waste rock, was flowing down this stream in France, basically, because she thought the uranium was in oxidation state 4, and typically people think uranium oxidation state 4, that's all right, it's insoluble, but she was interested in looking at whether there were actually colloids that would move down the river stream because they were carried on other small particles. So this is actually the first report. This was in Nature Communications last year, and it's the first report of mobile uranium-4 effectively in the environment. And so there were pretty high concentrations of uranium in some of this rock. She took samples along the riverfront. This is a sample holder of the type she used. This is our B18 cryostat holder. This is a Nalgene tube which you can put your sample in, and the Nalgene is effectively transparent at the uranium edge. So she had poor water samples which were frozen in there, and also some soil samples from various. She took soil depths basically. She took core samples from spot A and spot B to do the radioactivity, and these are just some of the results. So here is the Zanes, which this is a uranium-4 standard, this is a uranium-6 standard, and you can see that all the uranium seems to lie under the uranium-4, so it is reduced, and it fits to an aluminium phosphorate sort of environment. It fills with a phosphate, and it's associated by sort of elemental analysis with iron, silicon, and oxygen as well. So you've got these colloids that seem to get carried away in the stream and therefore flow downstream. So even though it is uranium-4, you see uranium accumulating quite a long way downstream because of colloid action. Moving on to microfocus and nanofocus at Diamond. On the I-18 X-ray microprobe, which I run, we can run from sulfur to molybdenum upwards and also from tin upwards. So there's sort of a bit of a gap on where the L3 lines are really very soft and we can't reach the K lines basically. So it's really hard to work on things like silver on I-18. It's not impossible, but it's just really hard and our sensitivity is down. We can get down to a beam size of around 2 microns. We can do 2 and 3 dimensional X-ray fluorescence, X-ray absorption spectroscopy, and also X-ray diffraction. So we can do X-ray diffraction tomography. We've just started doing in the last, say, 9 months. Had our first paper out in PCCP on that about a month ago. And we can also use Dane's 2D mapping, which is also a technique they use a lot on IO8, which has a much smaller beam size. 30 to 100 nanometers. It's normally the samples in vacuum, though you can make a sandwich parcel, as I'll show a bit earlier. It can scan carbon and higher elements, so it's looking at softer edges. It goes up to 4K, so it can just do the calcium K edge, and that's when you don't want to be run up, isn't it? Especially by someone trying to sell you PPI insurance claims. So just a quick on X-ray fluorescence, which I'm sure most of you know. X-ray fluorescence, if you've got enough energy in X-ray beam, when it hits an element, an atom of element, it can kick out a core electron to fill the hole that's created. An electron drops down from higher energy, has to lose energy as it goes from here to here, loses energy in the form of a characteristic energy photon. So if you have a discriminating detector, you can tell what element's coming off your sample. That works really well in the sort of higher energy regime, works less well in the lower energy regime, but and that's the voicemail message. Less well in the lower energy regime, where the fluorescence yield is considerably lower, but on 08, they do have fluorescence available, and for some things, as I'll show in an example of arsenic, it is really useful because when you have lots of L and lines, they can overlap with some of the K lines, and therefore fluorescence can really pick out the element a bit better than transmission, and it also can go a lot more dilute. So micro XRF, this is some of the setups we use on I-18. That's the actual setup. So that's the fluorescence detector looking at a sample which is on a stage there. The X-rays are coming in here. We have a video microscope which can look at the sample, and this is the sample stage which moves the sample through the beam to build up your two-dimensional map. And there's also a rotation stage for when we're doing tomography. This is more the tomography setup with the sample in a capillary, though this is actually an empty capillary during testing. But you can see much the same principle, detectors there, beam coming here, microscope there. Also, we look at thin sections. This is a thin section of some calcium carbonate worm granules which have been polished down, and actually this slide, though it's very unobvious from the photo, has a hole in the back of it, so the granule sits over a hole, which means we can do diffraction and Zanes on it at the same time. And then this is a silicon nitride window, so that's a standard slide, so that's I think a 2-inch by 1-inch slide. This is a 10 millimeter silicon nitride window with a 200 nanometer. So the window itself is probably a millimeter thick, but the slide is a millimeter thick, but it's got a window which is 200 nanometers thick, so you can put grains of dust or whatever on there and do diffraction as well in the same way. The beam's divided in 2 dimensions, obviously, on most X-ray sources. So the sample voxels, if the sample's really thick, you lose all that spatial resolution effectively, unless you're not really penetrating. So most samples need to be thin in some way. Micro XAS, why do people do it? Well, it gives less of the average pixel in bulk XAS. Bulk XAS of multi-component systems is really hard to look at. If you get to more than 3 components, disentangling it even by linear combinations can be hard. Ab initio is almost meaningless at the 3-component stage. So if you've got sort of soil, then micro is often the way to go, because you can look at the individual and then use those perhaps to linear combination, fit your bulk XAS spectra or something like that. But often samples in a beam, I was reviewing a paper only this week which was advocating using big beams rather than small beams, because it said small beams has a much better at not wrecking your sample, because you've got a much lower photon flux density on the actual bit of the sample. So even though I-20, well, say B18 has maybe about 50% less flux than I-18 at our best, its flux density is over a millimeter rather than over a 2 micron square, and so the speed your sample will reduce at is generally much slower on B18 compared to I-18. This is just an example that cooling does help. We do have a cryostat, though, not for using diffraction on I-18. So at minus 100, arsenic stays much the same at room temperature. It doesn't stay much the same in an organic matrix. This is an example of some micro XAF, one of the 2 uranium experiments we've done on, 3 uranium experiments we've done on I-18. This is the one we actually did on the Env-Rad-Net school. I just thought I'd show an example because it's sort of the nearest thing I have. Well, it's the only thing I have for needle's eye samples, I guess, which is of relevance to low rise. And so this is some mapping of a thin section that the BGS provided, and this is a plant root, a fossilized root, and the uranium actually, if this pattern had been done at slightly higher resolution, you can resolve the cell structure in the root. Uranium there is in green. Throughout these pictures, uranium in green, iron is blue, and I think arsenic is sometimes red, though this is chalcopyrite. So here I think we've got iron red and copper in blue, and there's a chalcopyrite grain which has a little bit of uranium on the outside of, and we also collected some uranium from the edge of the chalcopyrite and near the arsenic region, and also in this uraninite grain. The uraninite grain is not very interesting. It turns out to be uraninite, which isn't very surprising, but we could tell the oxidation state, and this was a uranyl type group on the side of the arsenic, and on the side of the chalcopyrite, that was slightly higher, hence the data is a bit better quality than the uranium that was near the arsenic grain, which is rather dodgy data, and it's pretty difficult to determine much more that that's also a uranyl group. You can fit some iron in that third shell, but it's a little bit noisy, the data. This is a sort of study from the SLS. The SLS has a beamline micro-SAS which has a mode where it takes radioactive samples twice a year, and they can do neptunium. This is an experiment by Froelich et al., I think in Tobias Reich's group, and they were looking at how neptunium interacted with clay under anaerobic and aerobic conditions. Oppelinus clay is interested because it's from the site, the Montcherry test facility, which is a test underground lab in Switzerland, I think, and also it's clay is it's one of the prime sites for Swiss and a couple of other European where they might bury their waste. The difference mainly here is between the anaerobic and the aerobic. In the aerobic situation, this is the neptunium. Not much neptunium sticks. If you zoom into this section in this bottom corner, the neptunium isn't actually associated with any of the other metals particularly, and if you look at the EXAFs, it's all neptunium-5. If you look at the anaerobic section, then the neptunium is strongly associated with this iron particle, and some of the neptunium is reduced to neptunium-4, showing that in aerobic conditions the iron can reduce. And they also did diffraction on this and showed that pyrite was one of the things that helped reduce the neptunium. So I've got 15 minutes left. That seems about right. Okay, so this is just some more this is some electron microprobe compounding the XRF, because they can do silicon and sodium, which are really hard on a if you've got a neptunium sample, because the protection you've got on a neptunium sample effectively prevents the X-ray. So those are microprobe because aluminium's the same, but it's much the same. This is the aerobic, and you can see there's no real association between the neptunium and any of the elements. And they did some zones of the hotspots and saw neptunium-5 in the anaerobic, but not the aerobic. So I think I've said most of that. And this is a really nice experiment that Carolyn Pierce did when she was at PNL, looking at how microbacteria interact with uranium and iron in air in the environment. It isn't a batch experiment. So she's developed some microfluidic cells with sort of pillars in them. So these give you sort of pseudo rock environments where not everything is in linear flow effectively, and you've got corners and barriers that things hide behind and get stuck on. And how does that actually affect the interaction between iron, uranium in solution, and bacteria in particular? Does it, because obviously if you do a batch experiment, everything is perfectly in contact with each other. If you've got flow and the bacteria is hidden behind the pillars and the flow doesn't actually go where the bacteria are, you may not get the same reactions. So she's built these microfluidic devices, flowed iron and uranium through them, and built up a bacterial cord. So this is sort of like looking at, you get these biofilms on things like sands, gravels, and trying to understand how they might interact in this sort of environment. So the flow goes this way. These are 100 micron, these are 200 micron pillars, I think, so you've got pore space, and this is a fluorescence light microscopy. So what you can see here is, I think just see here, it's better on a less big screen, is that this is where the bacteria is. So that's fluorescence light microscopy, and here is the bacteria, and this is an X-ray picture. This is putting some uranium in, so this here black is uranium, and you can look and see that the uranium actually really matches where the bacteria is in the XRF picture. That's visible light microscope image fluorescence to see the bacteria, and you can see, that the uranium and the bacteria are well reduced, and if you do the microprobe stains, you see the uranium is being reduced to uranium-4. Then if you add iron, you get some iron precipitating in the network, and now you can see the uranium is reduced here, but it doesn't necessarily stay perfectly aligned with the bacteria. Here it really stays really well aligned with the bacteria. but you also, some of the uranium is not reduced here, some still uranium-6, so there's less reduction when you've got some iron around, basically. And if you do that at the bulk scale or on things, you don't necessarily see the difference, so you really need to consider how bacteria can reduce uranium-6 when there's no iron around, and also whether flow means that you're modelling actually, if you just consider the results from bulk synthesis, bulk reactions into your modelling, it may not give you the perfect results because the things hide in different places really, and so the reactions, not everything's going to mix necessarily in a pore flow through a sort of microfluidic environment. Here's an example from a Berkeley thesis of a parafilm solution. This is how they handle the net. This is a plutonium sample, basically, and these are the details of how they made it. I think that containment would work for us as well, so that's just a way of looking at plutonium absorbed onto a surface, and it works quite well, and it keeps the sample wet if you're interested in keeping the sample wet. So that's just basically parafilm and then sealed plastic bags, and you've got this washer effectively that's around the sample, enables you to do micro studies. We do micro XRD and micro Zanes on I-18. So this is a calcium carbonate granule, similar one as you saw on the slide earlier, and we can do the diffraction and the Zanes mapping and compare it. So this is looking at calcite, baterite, and mixed phases between them, and compare the Zanes results and the diffraction results. And luckily, to a large extent, they agree, and we published that this year. In fact, scanning X-ray microscopy is basically, so this is a nanoprobe work on I-08, involves zone plates. We were using mirrors before, and you move the sample in front of the beam. These are the fluorescence detectors, and then you can detect in transmission where you get both phase contrast and absorption information, and you can collect the fluorescent signal away, and you map the sample, move the energy, map the sample, move the energy, and build up a stack of Zanes scans by plotting through your energy axis, your third axis. Sample holders I mentioned, if you want them for wet cells, there are some commercial examples like this Lux cell wet cell, or you can make silicon nitride. The silicon nitride windows I showed earlier can be glued together, and you can put a wet sample between the two because you have to seal them because the whole thing is in a vacuum. Your sample can't really be much more than a micron thick for the X-rays to go through it at these sorts of energies, especially if you're working near the carbon edge, so trying to image bacteria. This is an example from the group of French et al. Looking at manganese and uranium presence on the membrane of this CN32 Shellwanella bacteria. They looked at the fluidity and the fatty acid effects of the manganese, and they were also doing vanadium, and they basically and also assayed where the thing was. So that's just a picture of the bacteria. You can see it's a micron big, so you need quite good resolution to be able to study the edge of it. This is a manganese image, and that's the cell image, and you can see that manganese is associated with the cell quite closely. And if you do the spectroscopy, these are MN4, MN3, and MN2. You can see that the L-edge data clearly tells you that the MN is still in oxidation state 2, so it hasn't been oxidized. And they're trying to understand how the cell stability changes as you add metals around. And there's a similar example on arsenic on bacteria. So this is a fluorescence example. So you've got, this is a transmission spectrum here, the X-ray absorption, so you almost see no arsenic, but if you do the fluorescence yield, you can see the arsenic, because the arsenic, so if you're really dilute, this is arsenic associated with these iron metabolizing freshwater bacteria. Here's the arsenic map, and here's the SEM image, and you can see that the arsenic is clearly going around the side of the bacteria, while in transmission you'd never see that. So I-12 will go up to about 100 keV, does longer objects. I-13 is Peter Lee's domain, so he's going to explain what computed tomography is. So I'm just going to show this final image of a recent publication on a fossil of a cone. I think it's a pine cone that was done, and you can see the ovules. This is a reconstruction done from 70 keV data, and you can see that these are the ovules in the cone really nicely in some of the images. These are some of the data on exposure. I guess that the big advantage of synchrotron tomography. It's much faster, and if you go for some of the slower, you can get quite a lot more detail. So these are various of the cell detail from a slice longitudinal section through the complex, and that's a millimetre. So you can get finer detail. You can get down to sort of tens of microns resolution on I-12, I think, maybe even 1 micron. And that was all I was going to say.
Burning questions for Fred Roy? Got a couple of minutes if we've got questions.
Just a question for when you do the analysis in terms of to preserve the oxidation states. Do you do them normally to kind of cryo?
We tend to try and do some. For plants matter, yes, you almost have to do cryo or bacteria type systems. For sort of minerals type studies, we don't do a lot of cryo but it depends a bit on some elements are much more photoreductive or photosensitive than others. So arsenic in particular is very photosensitive, manganese is photosensitive. Some elements are a bit more stable, but you can always test by just sitting at one energy point and seeing how the absorption chair, if you sit near the edge, that's the best way. It depends on the sample as well. I mean, our samples for cryo have to be a bit smaller and fit in our cryostat, obviously. Well, we can look at almost anything that's not in our cryostat. For fluorescence tomography, unfortunately, we had a LRF failure on the synchrotron, so we haven't done this yet, but we hope to do it next year now. We were going to do our first cryo plant experiment where they put a root in a plastic capillary, and then you fire a cryojet down the axis of the capillary from the top, which means that we've done experiments with the cryojet before, but for mapping they're fine, but for any spectroscopy the sample actually moves too much in the path of the cryojet to make it useful. But apparently we were told by some people, if you turn the cryojet and fire it down the axis of the capillary, then it doesn't move because the capillary doesn't compress, obviously, in that. You're firing down the top of the rod. But we haven't done that experiment yet, so I can't say that works perfectly till we actually do it, but we hope to do that next year.
Have you ever run the same sample on different beam lines? Have you got a good way of knowing where you are on that sample? If you were to
Currently not enormously, unless it's got really good features that you can see in optical microscope or something, because, well, obviously IO8, because it's on a 10 nanometer scale, while we're on a or 10 to 100 nanometer scale, we're on a 2 micron scale. The scale difference is so big that the IO8 resolution is almost, well, it's a different order, isn't it? So we do have we have microscopes, and in infrared terms, we do have some tie-ups with the infrared beamline B22, where we can use the same sample setup, because slides work quite well on both beamlines, but not as well as we'd like.
Quick one, Fred.
Yep.
Before you sit down. Rapid access.
Yes.
For no radioactive samples.
No, they've got to be.
That's all.
They've got to be safe samples that you can handle just leave on the beamline unattended and what have you, because they basically put them on a carousel and set them to go overnight type thing.
Thank you again, Fred. Okay, so next up. Moving through. Go, you're doing it.
Yeah.
Sorry.
We could now give a double team.
Okay. We've got tag team talk now, so Steve's going to start us. Steve's going to be talking about things that we can do at the ISIS facility in terms of the use of neutrons. Thank you, Steve.
Down the bottom. It's very stationary at the moment. Unless that's on the bottom of the window.
Oh, there we go.
My name's Steve King, and I'm going to take a much lower level view than Fred did, because I'm going to guess that most of you are unfamiliar with neutrons. So I'm going to sort of try and give you an idea of why neutrons might be interested, and if you've got more technical questions, then we can talk about those as the day goes on. So ISIS is at the other end of the site. This is ISIS down here. Okay, you can recognise the diagram where we are at the moment, and all ISIS is a source of neutrons. Okay, but it's a source of neutrons based around a particle accelerator, which stems from the history of this particular site. Okay, and it's an alternative way of producing neutrons to using a nuclear reactor, which is what, for example, they do at the Institute Larry Langevin in Grenoble. Now, the ILL is another source of neutrons, which, as UK researchers, you have access to. Okay. If you come on the tour this afternoon, you're going to see something that looks a bit like that. So this is inside our what we call Target Station 1. So this is our first experimental hall, and come the middle of December, we'll be celebrating 30 years of the production of neutrons in there. Okay. This is the actual target station itself. So sat in the middle of that is a chunk of metal about that big, and what we do is we fire a high-intensity proton beam at it, as I'll show you in a moment. That basically chips the neutrons out, and then they get directed down beam lines into the instruments. So I have a little video. So we start off, we take hydrogen gas, we add an electron to it to make it H-. We accelerate that, feed that into a short linear accelerator, which gives those ions a kick. And then we inject them into our version of a synchrotron, which is much smaller than the diamond synchrotron. And as we inject them, we actually strip 2 electrons off, so they go from H- to H+. H+ is just a proton. Just like the electrons in a diamond synchrotron, they'll do thousands and thousands of orbits in our synchrotron, and each time they go through an RF field, they get more and more energy. And we actually increase their speed to, for the Star Trek fans in the audience, something like warp factor 0.8. At which point we better do something with them, or they're going to decay. So what we do is we kick them out of the synchrotron. See, they're getting faster and faster and faster. There we go. I've kicked them out of the synchrotron, and they hurtle down to the target station. On the way, there, they actually produce some muons as a byproduct, but then we're producing the neutrons there. We now have 2 target stations, so we're well on the way to doubling our capacity of instruments. So that's the basis by which ISIS works. Neutron scattering is not new. People have been doing it for the best part now of 50, 60 years. Okay? The gentleman on the right there is Cliff Shull. In 1994, he got the Nobel Prize for Physics with Bertrand Brockhaus for the development of neutron diffraction and neutron scattering. Okay, so in fact, neutron scattering is almost as old as synchrotron X-ray studies. I think the first demonstration of a synchrotron was in the late 1940s or something like that. Probably the message I would like you to take home is that neutrons and X-rays are best considered complementary probes. And what I've got here are 2 pictures in conventional visible light, and then in infrared. Okay. Now that's basically, those 2 images are basically the way that everything Fred was talking about works. Okay, there is a difference in wavelength here. A difference in wavelength, if you're talking about photons, is a difference in energy. Okay, and so you're effectively looking at the world at 2 different energy ranges. And what you can see is that there are some things that there is some level of detail which is the same in both images. For example, how wide the road is, maybe how long the road is. Okay, but in one of them, some of the fine detail is actually different. Okay, and that's the sort of message I would like you to take about neutrons. So the question is, how does that arise? And that arises through the properties of the neutrons. So they're a neutral particle. That means that they are non-destructive. And it also means they're highly penetrating. So we, from the point of view of doing anything with radiation, we can encapsulate a sample inside a metal can or something like that. That would be really problematic for X-rays. It's not usually a problem for us. Okay, so you can actually put your sample in some quite severe environments. The reason that neutrons and X-rays are complementary is in the mechanism by which the neutrons are scattered. Okay? Light and X-rays are scattered by the electron clouds around atoms, but neutrons are scattered by the nuclei themselves. Okay? Fundamentally different. Now that actually means that we are sensitive to the light elements as well as the heavy elements, whereas of course in X-ray scattering it tends to be the heavy elements that dominate your scattering. It also means that neutrons are sensitive to different isotopes of the same element, which X-rays are not. And depending on the technique, that may allow you to use something called contrast variation, which I'll come on to in a moment. We can produce our neutrons to have similar wavelengths to the X-rays, for example, that you get here on diamond, as I'll show you in a moment. So that means you can do diffraction type techniques. But for a given wavelength, the neutrons have much, much lower energies. Okay? Not thousands of electron volts, but milli-electron volts. And that actually means that the neutrons are actually very good for looking at biological material because they're not going to fry it. I'll show you an example of that at the end. And the neutron is a spin-half particle, so it will couple with magnetic moments. So if for some reason you're interested in magnetic properties of materials, neutrons are a good thing to use. This is just a collection of images of some of the different types of sample environment. So we got diamond anvil cells up there for doing things at high pressure. There's a slightly lower pressure cell there. If you were doing solution work, we typically use quartz cuvettes, just like you might use for UV vis work, for example. I had a user come along and built a microwave reactor down in one of the beam lines there. This is laser heating. So there's a pellet of the material is suspended on a gas jet, and then it's being hit with a really powerful infrared laser in order to get it to really, really high temperatures. We can do things like put commercial benchtop rheometers in the beam line. If you're using furnaces or something like that, then metal cans, for example, and cryomagnets if you're interested in the magnetism. So just a collection of images to give you a feel for the sorts of things that are possible. This is reinforcing what I was saying about the difference in the mechanism of interaction between neutrons and X-rays. Okay, for the X-rays, you're looking at the blue dots. So for hydrogen and deuterium and tritium, X-rays really don't see them very well at all, but X-rays are very good at looking at the high atomic number elements. In the case of neutrons, and I've had to actually blow up the cross sections by a factor of 5 to put them on the same scale here. Okay, you can see that with the exception of something like normal hydrogen, you have this rather irregular variation in the scattering power across the periodic table, and that's what allows you to look at heavy and light elements together in a material. But if we just take, for example, hydrogen, so normal hydrogen, deuterium and tritium, you can see there is a difference between those. So if you substitute one for the other, you will see differences in the neutron scattering. Hydrogen's a very common one that people substitute, doing deuterium for hydrogen exchange, but you can do it with other things. We've had people looking at, for example, at the Nafion membranes that are used in some chemical processes. They're nickel-based, and there's about 5 different nickel isotopes you can put in there, and you will see differences in the neutron scattering. I mentioned the technique of contrast variation. That's basically the neutron analogy of doing refractive index matching. Okay, collection of glass beads in air, you can see them easily. You put a liquid in there, they start to go a little bit fuzzy. If you change the liquid so that it starts to have a refractive index that's very similar to the glass beads, they disappear and they start to disappear. And if you can really optimize the matching of the refractive index, they really disappear. We can do exactly the same thing with neutrons. The example I've got there is that what you're doing is using mixtures of normal water, light water, and heavy water. And the example I've done there is just some sort of generic environmental sample where you've got something that's a bit mineral, which I've called clay, something which is natural organic matter-like. Okay, you look at it, start at the other end, you look at it in normal water, you'll see everything. You get to a point where you've put about 35% heavy water in there, and what's actually happening is you're doing what we call matching out, and you're matching out the organic matter, so all you see is the mineral. You add a bit more heavy water to the system, and now you match out the mineral so that all you see is the organic matter, and then by the time you get down to the other end where you're in totally heavy water, you see everything again. That's a very common type of experiment that the physical chemists will come and do, and the biologists will come and do, for example. You can play a similar trick though with other elements. So for example, some of our instruments will actually use metal cans which are a mixture of titanium and zirconium, because those metal cans will not scatter the neutrons if you mix the titanium and the zirconium in the right proportion. So just like X-rays, we can do diffraction and spectroscopy. Diffraction requires that you have wavelengths that are comparable to the distances that you want to study. So of course, if you're trying to do crystallography, you're looking at, you know, something like sodium chloride, you're looking at a bond length there of 0.2, 0.3 nanometers. So as long as you make your X-rays or your neutrons with a wavelength of that sort of size, you will see crystallographic diffraction. Obviously, if you're looking at something that has structure on a longer length scale, several nanometers to tens of nanometers, then we can produce neutrons on with those sorts of wavelengths to study those larger macromolecular type of structures. We can also do spectroscopy, but as I was saying, there is a big difference between the energy of the neutron and the energy of an X-ray photon for a given wavelength. Okay, so the large numbers here I've put in wave numbers because I thought they might be a bit more familiar to you, but the numbers in italics are the actual electron volts in whatever units. So, for example, something like ultraviolet spectroscopy that you might do in your laboratory, that's pretty high wave number, and looking at that table you can see you can only really do that with X-rays, which is exactly what Fred was talking about. Okay, so the sort of chemical spectroscopy that they do at Diamond, that's why. Okay, because the X-ray energy is matched to what you need to look at those electron shells. Conversely, however, if what you're interested in is the sort of molecular spectroscopy that you do in the lab with an IR or a Raman machine, you can see from those sorts of numbers you're going to struggle to do it with X-rays. However, you can do it with neutrons, providing you're using neutrons of about the right sort of wavelength. Okay? So you can do molecular spectroscopy with neutrons. We can't do the chemical spectroscopy that you can do with X-rays. So there's an example of the complementarity. And the other thing I'll draw your attention to is that typical bond strengths are usually a few thousand milli-electron volts, which are comparable to the sorts of energies of our neutrons. But those bond strengths are much, much lower than the energies of the X-ray photons, which is why X-rays are very damaging to, particularly to things like biological material. Oh, and the reason there's a big picture of Concorde here is because Concorde flew at about twice the speed of sound, 600 meters a second. We can produce neutrons that cover that sort of range of velocity. Okay, neutrons do not travel at the speed of light. So 5 angstrom neutron would actually beat Concord across the Atlantic. This is what we have at ISIS these days. So I showed you a picture of Target Station 1 earlier. That's our original experimental hall. And 5-6 years ago now we opened Target Station 2, and we're gradually populating more instruments onto there. We have about 16 diffractometers, I think, at the moment, 5 reflectometers, and then the rest are spectroscopic instruments. And we can do everything from crystallographic diffraction all the way up to macromolecular scattering, okay, polymers, biological molecules, that sort of thing. Reflectometry, they do have X-ray techniques that do something similar, and that's bringing either the neutron, the X-ray beam into a very small angle and looking what's reflected off of it. So that's useful for studying surfaces. So if any of you are interested in, I don't know, corrosion, for example, or something like that, might be an interesting technique. And then the spectroscopy, as I say, most of our spectroscopy is more towards the molecular, but we do also have instruments that can give you information about phonons. So those are the acoustic modes that are important if you're interested in the thermal properties of materials, and we have spectrometers that can study excitations, which are the things that are important if you're interested in conductivity within materials. But here's the but. Okay, there had to be a downside to all this, and the downside to this is that we cannot produce neutrons with the same sort of brilliance that you can produce photons. So the laser pointer in here, for example, is probably producing something like 10 to the 15 photons a second, which is fairly comparable to the sort of X-ray photon brilliance of a diamond beamline. Unfortunately, with neutrons, we're several orders of magnitude down. So we can't do the very high time resolution experiments that you can do with X-rays. Our counting times, we can do experiments on timescales of seconds if it's the right sort of sample. Typically, you're looking at minutes to hours. We can't do really, really small samples. Well, we could, but then you drop the count rate even further. So our samples tend to be larger than the ones that you would use in neutrons. That may not be a bad thing, of course. It may give you a better bulk average than the X-rays would. And sometimes people will deliberately come and do the neutrons for that reason, because the X-ray scientist doesn't want to defocus his beamline. And we will also try and make the most use of those neutrons that are diffracted or scattered or whatever by using larger detectors. So an X-ray detector might be this sort of size. Okay, my neutron detectors may be this sort of size. But as I've said at the bottom, we always like a challenge. So if you've got an idea, at least come and talk to us, and we'll tell you whether it's crazy or not. So just to summarise, neutrons are a non-destructive probe. We can exploit differences in scattering from different isotopes. So they're great for bulk measurements or looking at things in quite complicated containers, for example. Best regarded as a complementary probe to X-rays and neutrons. We can do structure and dynamics just like X-rays. We can do molecular spectroscopy just like light and X-rays. We can do radiography and imaging, as Winfried is about to tell you. It is possible to get some chemical elemental composition data out with neutrons. We can't do it, unless Winfried corrects me, we can't do it at ISIS at the moment. They're a good probe of magnetism, and you can probe the thermal and conductivity properties of materials in spectroscopy. What we can't do is do really high time resolution experiments. We can't do microscopy of the type that Fred was talking about, okay, and we can't do the chemical spectroscopy. Those are the differences. One very quick example was some work that we haven't quite finished to the point of writing up yet. So Stephanie Handley-Sidhu from Birmingham. This is a bacteria, and the bacteria actually has a phosphorylase enzyme in its outer cell wall. And that, if you feed it the right sort of cations, it will actually produce phosphate. So if you feed it calcium, it will produce apatite, hydroxyapatite. Okay. On the other hand, if you feed it strontium or calcium or cobalt, it will form apatite with the strontium and the cobalt sitting on the atomic positions that the calcium would normally take. So the idea is this is a field deployable way of remediating contaminated soil. And actually, the reason that we haven't written this up yet is that Stephanie got whisked off to Fukushima about a year ago to actually try this for real. Okay. But what we did was an experiment where we actually put the bacterial system in the neutron beam. This is a neutron technique called small angle neutron scattering. So it's looking at relatively large length scales. It's looking sort of the 1 to 100 nanometer length scale. Okay, and then we fed it something that would allow the formation of the hydroxyapatite, and with time you can see that we actually see an increase in the scattering here, and it actually obviously reaches some form of limiting level, and from that we should be able to get some idea of what the kinetics actually was. The example there, you can actually see it does actually form crystals. Right, I'm going to hand over to Winfried now, who's going to say something about neutron imaging, and that really is a slide, that is a neutron radiography slide looking at plant roots, but I'm sure Winfried's got far better examples.
So I actually only want to add to Steve's presentation and tell you about our options and plans on the engineering beamlines. And we have a diffractometer, a strain scanner, Nginx, that we use since 2002, and that we use for residual, basically more or less for exclusively for residual stress, strain and stress analysis of metals and alloys to study joining techniques and so forth. So I'm instrument scientist of a new beamline called IMAT. IMAT stands for Imaging and Materials, and it's actually not. We are just installing it, and we hope we will have first beam in summer next year. So I will mostly tell you what we are going to do on this beamline, but also refer to Nginx. So here's a schematic of the beamline. Beam is actually coming here from the left. We have a sample. We will have a choice of imaging, neutron imaging cameras. And what we want to do is conventional neutron radiography and tomography. But we also want to exploit the specialities of our source, and that's the pulsed source and time-of-flight diffraction. So we have some options for some new energy-selective imaging techniques. And then, not next year, but eventually we will actually build up large arrays of diffraction detectors, and we'll use those to do bulk, strain, and texture measurements, and do that also simultaneously. And typically, like on Nginx and also on IMAT, we will do that in situ measurements. Typically, we work at, for example, at high temperatures. So just to show you that we are actually still building. So we have, so that's the IMAT transport neutron guide that we are used to transport the beam from the isosecond target station into an external building. And we are still constructing, so we have just put up the radiation shielding around the experimental area. It's pretty empty inside here, but we will have everything ready by next year. Assuming that you will potentially be mostly interested in the imaging part of IMAT. So here are the main parameters. So we will work with a wide beam, but we will have the option to do very good or a good energy discrimination. The beam size is 20 by 20 centimeters maximum. If samples are bigger, we will need to scan. And the spatial resolution that we aim for is 50 micron. So that is not as much as you will get with the X-rays, of course, but the reason for this resolution limit is what Steve said. It is the intensity that we have available. Okay, so here again the main components in the experimental area. The main point here is that we will have a heavy-duty sample positioning system, which can move samples up to 1.5 tons, and then the cameras. Initially, we will actually, and also next year, we will have a selection of cameras and a small numbers of diffraction detectors. And in the second phase, that will be a year later, we will build up detector arrays, first at 90 degrees and then later also at other angles to do the diffraction scans. To give you scale, actually, the size of this camera is 1 meter in height. And then we surround the equipment and the sample area with shielding, with a roof that we can open so we can crane in heavy samples and equipment from the top. So what are our options on IMAT and NGINX? So we have the transmission mode, so we want to do wide beam imaging and conventional radiography, tomography, but then also measure as a function of energy, so energy selective radiography, tomography. And I will show in a minute that will allow us actually to do a kind of microstructure analysis, so we can, for example, map strains in this, in the nickel bolt, for example. And then we will have the diffraction applications, or the diffraction options for quantitative phase analysis, strain stress analysis, and texture analysis. And we want to do this also spatially resolved. And that will be on a level of millimeters. 1-2 millimeters for the diffraction analysis, and that compares to the 50 micron that we want to achieve on the imaging side. So I show here some examples. Most of them are not for IMAT, but from other imaging facilities, just to show you the breadth of application that we will cover on IMAT. And I want to highlight two aspects that distinguish us from the X-rays. One of it's a non-destructive testing of bulky material. And neutrons have, as Steve said, have the high penetration power, so we can look into bulky components like this diesel injector nozzle, and we can actually follow inside the flow and distribution of the fluids inside the component. And then again, a very typical example for neutrons, we can see organic materials, in this case flowers, in the interior of a thick-walled brass statue, something you couldn't do with X-rays. And we can determine distributions of minerals in rock core samples, in concrete or fossils. And that works particularly well, again, if the minerals have contain hydroxide groups or or water groups. And that brings me to the other important point, and it is localization and of hydrogen and determination of hydrogen distribution. So we will certainly use also the beamline to determine diffusion coefficients and hydrogen distributions in metal alloys and steel, zirconium, to look at effects like hydrogen embrittlement, measure the extent and locations of hydrogen blisters. And here's another example, like the one that Steve had on this last slide. So we will use neutrons to determine flow in soils of water in soil and plant roots, and look at the capillary transport. And then also more generally look into the uptake of solvents, water, fluids into porous media like polymers, gels, compacted clay. So that's a traditional application. We want to go this one step further and then use our fourth dimension, that is the neutron energy. And what we, for example, if we have a metal sample or an alloy sample with a crystalline structure and measure in transmission, what we see in each of our pixel is actually a spectrum, and transmitted intensity as a function of energy or wavelength, where we have a structure and we can exploit this structure. And what we will observe are the so-called Bragg edges, which are basically nothing else but effect of neutrons Bragg scattered out of the beam. So we see those as edges in the transmitted beam, and then we can analyze the positions of edges, translate those positions into strains. We can analyze their height and relative heights and determine compositions and get information about texture of the material, and look at also the width of an edge and determine particle sizes and microstrains to a certain extent. So for us it's important to actually analyze those Bragg edges, and this is actually the energy regime of IMAT. There was one comment by Steve about the elemental analysis. We actually are starting now a little pilot project to also use faster neutrons to determine elements in the bulk of, again, typically will be of engineering archaeological materials. So just one example of what it actually means in practice, and we are already testing our cameras that we want to use next year on IMAT. We are testing them already on Engine X. And here's an example of steel die, basically a lump of 5 centimeter, 6 centimeter thick steel that we measured on Engine X. And here actually two steel dies next to each other. And what we see is here that with wide beam techniques, we see that it's pretty hopeless and we don't get much information out of it. But as soon as we measure as a function of energy and analyze the Bragg edge positions and the width of the Bragg edges, we start to see phase transitions from the martensitic phases on the outer skin to ferritic phases in the interior. So that's what we want to analyze. We collect kind of the complementary information in the diffraction data. We again see this martensitic to ferritic transition. We also pick up other details in the diffraction, like extra phases, the austenite or the iron carbide phases, which we don't see in the imaging. And it's actually just a question of concentration. So here my point, and that is also the purpose of IMAT, will be that we need actually both. We need the diffraction, where we measure with a lower spatial resolution, what we pick up just more subtle structural details. With a spatial resolution, let's say, of a millimeter or 2 millimeters, but we still need the imaging techniques to map the main parameters with a higher resolution. And this is just to summarize our application range of IMAD and Engine X. Engine X typically covers more the hard engineering side, metals and alloys, also a bit on concrete. With IMAD, we want to tap into the soft matter applications, like the plant studies and the soft, the polymer studies. Here's some photos of experiments on Engine X, and experiments on IMAD will not look so dissimilar. So we have a lot of space to measure large samples and to bring in also sample environment equipment to measure, to run projects in situ. Which doesn't mean that you can't come with the small samples. I mean, we measure also much smaller samples than these. Okay, so these are my slides. So if you have questions, we can maybe discuss over. If you have questions now, I'm happy to answer, or I can answer questions over lunch. I'll show you to the instruments this afternoon.
Just a quick question. I mean, I think we have an Imperial College, we also have a CT scan in neuroscience, which tries to do the similar aspects in terms of the water flows. I mean, how complementary are they in terms of tracking information?
Yeah, you can. You can follow water flow also in. I think I've seen projects in rock samples as well, and I've seen pretty convincing studies of that as well. I think what we will neutrons just have again a bit of a higher sensitivity to water and hydrogen. That's one thing, and the second thing is we can, as Steve said, we can run, we can put these samples also in containers and maybe do more in terms of also in situ fluid flow analysis. I'm aware there's also nowadays, especially with the flux that you have on the synchrotron sources, and maybe also with many lab sources, it's not impossible to do these kind of studies on the X-rays. I probably need to also, we need to collect a bit also more, increase our expertise and see how much better we can do on the neutron imaging side. So I can't give you a quantitative number.
Just forgive my ignorance, in the list of things, in your presentation actually, things you can and can't do. Can do molecular spectroscopy, can't do chemical spectroscopy. What just definitions go into the different experience?
Molecular spectroscopy is the sorts of things that IR or bond vibrations, rotating modes, that sort of spectroscopy. It's not telling you the higher energy dissociation type spectroscopy that Richard's on.
The other thing was kind of flight method is so much slower than the X-rays. What specifically does the ability to do time-to-flight measurements give you with different imaging?
It's actually, what we actually do is we measure the energies of the neutrons via this time-of-flight measure, by a flight time measurement. So that's actually what our detectors do. That the measured variable is the time, from the generation in the source up to the detection in the detector. That's right. So, for example, in the images, in the example that we showed, so we are not collecting one radiography. If we just put a sample in front, next year we will collect 3,000 radiographies, all measured at a different energy. And the interesting thing is maybe that sometimes it's also, especially if the material is not known, you can actually do the experiment and collect all this information in energy, and then and after the experiment, in the post experiment data processing, you can actually go through the data and try to pick up the right energies and to maximize contrast, even if you don't have, if you're not aware of all these of your materials when you do the experiment. Ideally, you know as much as possible about your experiment, but it might happen that you can still achieve a lot post-experiment.
The analogy would be doing an X-ray experiment where you're continually changing the monochromatometer and scanning images.
Okay. Thank you very much for your talk. I'm now going to hand over to Andy, who will give us our last talk before break for lunch. And lunch is going to be served in the atrium. So Andy works at the Central Lasers facility, and he's going to tell us about the different things that we can do with their techniques available there. And interestingly, along with Diamond, this is one of the places where Env-Rad-Net has had people in doing some experimentations. And Louise Matrojan from Manchester has been pioneering some uranium fluorescence work with the guys at the Central Lasers facility.
Gareth know a lot of the talk.
Pardon?
He seems to know a lot of the talk.
I've exhausted my knowledge there.
Thanks, Gareth. So as Gareth said, my name's Andy Ward. I work at the Central Laser Facility. What I'd like to do is to have a quick run through some of the laser-based techniques that may show potential for environmental radiation studies. So the format will be a quick introduction of the Central Laser Facility. Then we'll go for a whistle-stop tour of some of these techniques. Now I'm picking ones which I think are quite relevant to environmental radiation. Some of them I'm going to skip over almost straight away, but I'm going to try and work out and spend some time with those ones which I think are going to be interesting to you. I'm going to look at some of Louise Natrojan's work, some of the experiments we're doing, and maybe discuss how we can push some of these techniques in the future. So look at this thing. So the Central Laser Facility is roughly composed of two halves. I've tried to show it in the grey here and the dark blue here. So grey areas is high power laser experiments. It is lasers such as Astra Gemini, Artemis and Vulcan. These use really high intensity laser sources, very short pulse lengths to produce very high energy laser beams. It is particularly popular with the physics community. They want to study things like fusion energy, ion acceleration, plasma physics. Through discussion with some of the guys on the Environmental Radiation Network, this really isn't an area we should dwell too long on for this discussion. It hasn't really been highlighted as an area that's that useful. However, I would say we should keep a watching eye on this. They can do XUV generation, coherent X-ray sources, and beams of electrons. So in the future, these may actually provide some quite interesting sources for large-scale imaging. The Octopus and Ultra facilities, that's where I work, largely doing vibrational spectroscopy, based on lasers, of course, and also imaging and something called laser tweezers. We're based here. So currently we're set about there in Diamond House. This is the research complex to the side of it. The Octopus and Ultra facilities occupy the lower ground floor, or most of the lower ground floor, on the left-hand side down here. We have a suite of something like 20 different laboratories. We moved there in 2010 from the old R1 buildings. We typically run about 100 weeks of user access per year, and the ratio is about 40 of those weeks will go to Ultra, 60 of the weeks will go to the Octopus facility. So the layout, once we get inside there, effectively the Octopus, the imaging type facilities are all down one end. There's a central core of lasers, and they basically branch out into the different workstations, different microscopes to do various types of the imaging. Ultra is based around this very large optical table, to generate the main pump and probe sources. And again, the light then feeds out into other ancillary laboratories to do the experiments. We also have some work going on up here where we're looking at microscope and super resolution techniques. Occasionally we go out of the research complex restraints. We go to Diamond and also to ISIS and space science to do laser-based activities there. We have a multidisciplinary team, so physicists, biologists, chemists, mathematicians, even astronomers to help us do some of this multidisciplinary science. We have limited support laboratories. These do chemical and biological preparation. So first of all, we'll talk about the octopus cluster. So this is basically the imaging cluster. Effectively, I'm going to say a range of different techniques. We'll only actually settle and talk about the confocal techniques for the time being. So imaging techniques, so single molecule imaging, super resolution techniques, total internal reflection fluorescence microscopy. These are effectively all biological imaging techniques. The image on the micron, sub-micron level, but actually they've got quite a lot of complementarity with some of the imaging you might want to do on bacteria or radioactive species. Again, effectively there's just a central laser system in here, and that basically just reaches out to all the different laboratories, giving us multiple beams, different pulse timings. Basically it's a really flexible system, so we can tune it and adapt it to whatever the need of the user is. So let's give you a walk through single photon confocal microscopy. Fred already mentioned you did some fluorescence light microscopy in Diamond. This is run by a guy called Stan Botchway. So fluorescence microscopy, you deliberately put a fluorophore, a tag, into your cell structure, which normally latches onto something in there. And then you excite that fluorophore with a laser beam. It then emits at a different wavelength. You put an optical filter into place so you can only see that emitted wavelength. And from that, you can work out where your fluorescent tag is gone. So in this particular case, we've got a HeLa cell with nanoparticles in there. The cell structure is shown in red, nanoparticles in green. Okay, that's quite easy. The confocal bit becomes into how you collect the light. So we use a pinhole to collect the light coming back from the sample. And that's so we can really refine or define well the collection volume. So typically when you use the pinhole, you'll be collecting from a focal depth of only a micron, or even less than a micron. That's actually quite good. It reduces a lot of the scattering, background noise, stray laser light, etc. that's in the sample, so you can get a very well-defined image. You can do that for a range of different laser wavelengths, and you can pick your fluorophore of choice, so you can do lots of multicolour tricks with that. So often you find things in literature where there's maybe 3 or 4 different fluorophores going on, 3 or 4 different wavelengths, and you can basically just identify where everything is in the sample using that technique. The next step on from that is to start using pulsed lasers for the imaging. So you use the pulse laser. So now, instead of just having a sort of continuous wave laser, so you're always activating the fluorescence, you just give it a little pulse, you turn the laser off then, and you watch how that fluorescence develops. So if I point you to this plot in the bottom right-hand corner, this is called a fluorescence lifetime image. Well, this is the image. This is the actual decay of the spectrum with time. So the pulse of the laser would come in here somewhere. Shortly afterwards, you get the fluorescence. Pulse would go off, and you'd watch the fluorescence decay. Typically, that goes with either mono-exponential or bi-exponential decay properties. So you get a lifetime of that decay. So in this particular case, this is working. Yeah, you'd be looking at lifetimes of 2,000, 2,500 picoseconds. That's actually quite interesting, because that means as well as, if you can look at this lifetime, you can tell things about the molecular environment. That means the fluorophore, maybe the fluorophore's bound to something in the structure. Maybe the fluorophore's reacting, or the structure to which it's bound is reacting. Maybe there's a different viscosity or a different pH, which is changing the way the fluorophore's behaving. So you can actually get a very detailed information, not just on where the fluorescent signal is, but actually what that fluorophore is doing and the properties around it. Next stage on from single photon confocal microscopy, multi-photon confocal microscopy. Trick here is, in the fluorescence in the single photon example I showed, you use a laser beam, say a 400 nanometer laser beam, and that will excite the fluorophore. In this particular case, you can use a laser beam with double the wavelength, so say an 800 nanometer laser beam, and you use 2 photons from that laser beam arriving in the same place at the same time to excite the fluorophore in the same way. But you can actually do that at a significantly greater depth penetration. So you can get up to a millimeter in the sample. And that's because your wavelength of light is not absorbing, and also you're not doing any of the excitation of the fluorophore processes most of the time. You're waiting for a very statistically uncommon event, i.e. the photon arriving at the same place in the same time, to get the fluorophore. So this allows us to go deeper into the samples. This here is an example of that. This is basically an avian cell, which is the red and the blue areas, and the green is a fowlpox virus within that. So we go much deeper into the cell to get much better depth imaging. And we can also start to map more the molecular environment. So this here is quite an interesting image. It's a cell, in fact a cancer cell. And in effect, this has got a fluorophore in there which responds to the viscosity within that cell. So if you can measure the lifetime of the fluorophore, you can actually learn something about the viscosity of that. So in effect, this is just a viscosity map of the contents of the cell as it's dying through photodynamic therapy. So that's the background behind the FLIM techniques. And why I've discussed that is because Louise Natcham from Manchester has actually started using these techniques to start imaging bacterial species containing urinal compounds. So the top here, this is actually a copy of an In Brief. So In Brief is our STFC magazine. It's effectively highlighting the fact that these guys were doing research at the Central Laser Facility, basically looking at trying to characterize mapping of bacteria. This is the sort of result we're getting. So basically, this is a Geobacter sulfur reducens, which is taking up urinal 6 with the aim of seeing if it can reduce that to urinal 5 to see if the bacteria species can actually reduce the mobility of the uranium species in soil by reducing its solubility. To give you an idea of scale, you've probably seen this already. These are about 2 microns in length, 1 micron wide. This is a lifetime image of that. So the overall picture is of the order of 10 by 10 microns. So this is microscopy. We only deal with, most of the images you've seen, we'll be looking at a maximum field of view of something like 50 microns. Very briefly, I'll give a vague summary of the results. The work that Louise has done was based on 3 weeks access. It's been largely written up, and I think it's due for submission in the next few days. We can do single and 2 photon fluorescence lifetime imaging, or phosphorescence lifetime imaging, i.e. a slightly longer time scale on the decay, using confocal techniques. Clearly, we can image individual bacteria. From each bacteria, we can get emission spectra. So basically, we sit on that particular bacteria, look at the excitation we're doing at, say, 405 nanometers, and we work out the light coming back from that. So we've got the emission spectrum, and we can also measure lifetimes for each of the individual bacteria. So from that, we can show that the urinal 6 species is co-locating with the bacteria, and we also pick up there's changes in lifetime, which would indicate maybe binding events, maybe reaction events. Probably we need more work to actually make that an unambiguous conclusion. The work is ongoing. The group are actually in this week doing further studies on these sorts of compounds. But using radioactive material in the research complex at Harwell has actually been quite tricky. This is the first time we've done work on radioactive material in our laser laboratories. It took something like 18 months to get all the protocols in place and get all the various forms signed off and what have you. We've currently got 3 laser laboratories which are approved for use as radiation supervised areas. Currently, we're using sealed samples. So they'll be prepared in Manchester, couriered down, remain sealed all the time, and then go back to Manchester. The level is quite low, so we're typically holding something like 6,000 becquerels at any given time in the laboratory. So we're talking quite low level in terms of the content in some of these samples. But again, we're only imaging one bacteria at a time. So the low concentration, as long as it's in the bacteria, that seems to be working out okay. We have got potential for wet lab preparation. I've talked to the RPS in the laboratories. This can be done probably quite short time scale for uranium species. But if we start venturing out into other materials, then we need the various permits and approvals to carry on with that work. So for this to happen, we need quite a long lead time to get everything in place. We've also applied the FLIM techniques, so the lifetime imaging techniques, to rock samples. This is basically a quick look at effectively the rock sample under a sort of bright field image, rock sample under fluorescence lifetime imaging. So again, this was actually looking at the luminescence of the materials in there, and effectively, with a bit of tinkering, there's the capability there to start looking at the elemental concentrations in these samples using the 2-photon system at easily 500 nanometer resolution within that. So again, quite a detailed look at what these samples are doing. Move on now to another half of the facility, the ultra facilities. Now this is much more fundamental dynamics in terms of the molecules. So you're looking here really at vibrations and rotations, how the molecules get excited by some of the photons from the laser light. So as I say, probing vibrations, following the molecules as they react. Really two avenues to go: Raman spectroscopy, infrared spectroscopy. This one's absorbing and emitting and scattering some of the light. I won't dwell too much on this. If you've got any further questions at the end, I can spend a bit of time. But basically, various resonance techniques, time resolved techniques, transient techniques, depending really what you want to look at. So if you want to look at a certain feature in the molecule, you pick a slightly different technique. The same with the infrared. Time resolved, two-dimensional infrared techniques, photon echo. We'll actually just spend just a couple of slides on this one just to give you a flavour of what some of this spectroscopy can do. The ultra technique is basically very flexible. It's got multiple beams, multiple colours. You can tune in your timing patterns, tune in your pulse lengths. So the various tunabilities and pulse durations are here. It picks out changes, especially with the infrared spectrum. Basically 1 in 10 to the 5 is what it's using to look at the differences. From the perspective of using it for radiation type samples, typically we're solution based, and you normally hit these samples fairly hard with the laser beam, which means you have to flow the samples or basically have them on a raster stage so you're not hitting the same part of the sample too many times. So typical volumes we're looking at is the 20 mils for the sample to flow around, and the flow cell is here in this particular case. And we're looking at millimolar concentrations for any species you want to follow in that. So this time-resolved multiple probe spectroscopy. It's an example of one of the techniques. So I'll run through it so you get a sort of feeling for what's going on. It takes a pump laser source here to excite a molecule. Then the molecule will evolve, charge transfer, energy transfer, singlet, triplet states, folding techniques, whatever it may be. We then probe that state of the molecule at time scales after that, from femtoseconds, nanoseconds, microseconds up to milliseconds. So basically you're looking at the evolution of that molecule with time over, I think it's 9 decades of the time scale. This is what it looks like. This is with a tungsten carbonyl compound being probed. Effectively, these are the spectra we're getting from the kit. This is effectively what's happening. So we're basically triggering a reaction, watching the reactive molecules cool down on the 10 picosecond time scale, watching how it reacts with the solvent on the 100 picosecond time scale, and finally watching how the compound reacts with water on the 300 microsecond time scale. So again, this is all very fast dynamics, looking at some of the vibrational modes, how the things react, how the molecules change energy states. This is my particular area. It's actually using the lasers to manipulate microscopic objects. It's called laser tweezers or optical trapping. It uses laser beams, normally focused laser beams, which you balance the refractive effects and the scattering effects of the laser beam to capture an object. So typically it will capture things like beads, but it can also do things, mammalian cells, spores, bacteria, yeast cells, protein crystals. These are largely in fluids. You can also trap things in airborne particles, so aerosol droplets. There's an example I'll show later on as well of a solid particle. You can play games with a laser. You can tell the laser to go into different shapes, so it forms like a hexagon shape, or you can take your liquid droplet and deform it into triangles and squares. You can move your sample in 3 dimensions under the field of view, basically. You've got really good control, X, Y, and Z. Or you can move your environment around the sample if you've got a microfluidic type environment. For this particular, for the application here, I'm actually highlighting some of the work we do, combining the optical trapping with Raman spectroscopy. So basically we're looking at how the laser light interacts with the molecules. It's a vibrational spectroscopy technique. You'll often get a shift in the wavelength during the interaction, and the intensity of the shift is related to how the molecule's vibrating or rotating. So this is a Raman spectra of an optically trapped bacteria species. We can basically assign all the various peaks to nucleic acids, phenylalanine, carbohydrates, proteins, lipids. Typically this will take something like 30 seconds to acquire from a single bacteria. It enables us to be able to select and sort bacteria. So we can capture a bacteria, look at the Raman spectra, make a decision on what that bacteria is or what maybe it's encountered in its lifetime. This is with Wei Huang at the Creative Institute. So this is basically the fundamental for the Raman sorting technique. So effectively you capture, identify and sort bacteria. You have a groundwater source, so you basically have a completely mixed source of bacteria. In this particular case they were fed with a glucose containing carbon-13. And so just as an example technique, and so you can actually look at, say, capture a bacteria. The carbon-13 and the carbon-12 will give you slightly different vibrational modes, so you start seeing peak shifts. So you can actually capture a bacteria, look at the peak shift, say, right, okay, you've used the carbon-13, sorry, you've got carbon-13 inside you, you've used the glucose. We can actually save you, put you to one end of the capillary tube or microfluidic flow cell, and then send you off for cell amplification to tell me what bacteria you were, or you can try and actually go for incubation to grow up that bacteria species. So effectively it's a kind of aiming towards a bioremediation application, where you'd be looking to say, right, okay, what strains of bacteria are good at processing some polyaromatic hydrocarbon? I can see from the work that Louise has already done on some of the geobacter materials that this could also be used. We can combine this technique not with Raman, but with the fluorescence lifetime imaging technique. So you could capture a bacteria, look at the imaging of that, try and work out what species it's got inside it, and then be able to sort that off into different areas to try and work out what the species of the bacteria are that are actually doing the hard work in there. We can also study airborne particles. I'm not quite sure if that's, I can see why some of the water-based and dry ones might be interesting. I'm not sure if this is too relevant. It's something we're just really getting into. Basically, this is an optical trapping system. There's a laser coming from the top objective, laser coming from the bottom objective. They meet at that dot there. That dot has actually got a captured particulate in it. In this particular case, it comes from a medical inhaler. Size range of these things is typically in the 1 to 7 micron range. You can hold them for hours on end, and you can play all the tricks on spectroscopy, so Raman or fluorescence-based imaging techniques on these to learn a little bit more about what these things are doing in situ. Another variant on the Raman spectroscopy, something called spatially offset Raman spectroscopy. It enables you to acquire a Raman spectra through the walls of a container. So in effect, you have a detector here, laser beam coming down. If you move the laser beam from just before the container to this area, you excite a slightly different area in the cell, but you can still collect in this area where there's less diffusion going on. You can analyze bone beneath skin, drugs, or contraband inside plastic bottles, explosives inside containers, counterfeit tablets inside blister packs. It is currently, this is now developed into a spin-out company called Cobalt Light Systems. They manufacture scanners that you find in airports. So effectively putting your drinks containers inside these to probe them without actually opening the sample, to look to see what's inside them, get a Raman spectra. Inside here is basically a database of all of the safe, unsafe materials that people might be looking for, trying to put onto airplanes, and it can make a decision saying, yes, this is safe or this is not safe. We also do quite a lot of cross-facility research. The two examples here with diamond. This is with Nick Terrell on diamond light source, diamond I-22. He runs a microfocus beam time doing SACs and wax. Tucked away just in there is an optical trap. There's a capillary in that optical trap. And in that capillary is something that's caught in the two laser beams. It's a zeolite particle. Zeolite particle is about 10 microns in size. The microfocus beam line delivers a beam that's 10 microns in size. So effectively you can hold this particle in the beam line and get a scattering profile from there. Quite early days. We've done a few examples of this, but it's quite ripe for exploitation in terms of if you want to do further stuff. So effectively you would have to have an example where you're looking at colloidal material. I think Fred mentioned there's a river-based example before where material was being swept down the river. You want to imaging these small grains of the sort of 10 micron size to see what they were doing. You can change that slightly. We've done protein crystal harvesting. Again, it's using a laser trap to capture objects. This time it's protein crystals. So in effect you can sort the crystals. So this was actually a real mess before, much like the bacteria sample, but you can actually go and select the size and shape of crystals that you want. You can harvest them and put them into a separate area. And you can grab those crystals, put them into a micro mesh. Once they're on the micro mesh, you can then put them into the you can then freeze them and then put them onto the beam line, in this case I-24 for scattering. Again, looking at objects of the order of 10 to 20 microns in this context. So the last one I'm going to now show is much the same as one of Fred's slides, the facility access mechanism. We too operate on a 6-monthly call basis. Our next call is quite soon, 20th of December 2014. There's a peer review process, so there'll be a panel that sits and judges that. Typically you need 3 sides of A4. That might have changed to 2 sides this time round. Here's the website for if you want further information on that. Here are the cool, basically you go to the website, you come to this page and follow the various links. So this is the mechanism that Louise Natran has used to get access to the facility to do her work on lifetime imaging. She's now done this twice successfully. First time got 3 weeks, second time got 3 weeks of access. So this system works. The panel are, I would say, very receptive to environmentally based applications.
We can probably finish for about 4 o'clock then.
Okay, fine. Yep, no problem.
Okay, so we're going to have a final talk now from Peter Lee. He's the director of the Diamond Manchester Collaboration Centre. He's going to be telling us about the different types of techniques that we can do here at the Diamond Manchester Centre. So thank you very much for agreeing to come along, Peter.
Okay, thanks. So it's easy to actually just ask questions as I'm going through, because then I can actually tailor this to your own needs. What I'm going to try and do is, first of all, show you just a couple of ways you could use imaging in real space. And even with imaging in real space, you can differentiate some speciation, but most you can't. So you usually have to combine it with spectroscopy, which lots of other people have been talking about. I'm going to talk about both synchrotron, but also laboratory, because if you can do it in a lab, you can actually do more experiments. You can then just come, so almost all of our experiments, we do most of it in a lab, and we come for specialist ones that are very rapid to the synchrotron to augment that at the best, or to the neutron source. So I'm going to quickly go over and actually tell you how imaging and tomography works, so you know when it will work and when it won't work, and have an idea of what sort of situations it might actually help you with. And I'm going to give you an example at the beginning and the end. I'm going to start off with leaching, because I looked at some of your backgrounds, and leaching also ends up going and permeating through rock, being uptaken, some of the effluent. So there's a lot of analogies. I'm also going to go down into shales, where we go down into voxel sizes of 6 nanometers, and we do multi-scale, which might be important for some of your applications as well. And just summarize at the end with some of the potential impacts on geoscience. So why tomography? Well, very simple. In 2D, often what you see in 2D is not what you see in 3D. The nice thing is, if you use X-rays, you can also see inside as well. So you can see that wolf in a rabbit's clothing. So it allows you to do it. And why is that important? Well, you've got situations where you're looking at effluent or other things happening inside of rock, and you need to see in there. And so X-rays and neutrons are fabulous for that. What do they look like? It's always useful to sort of know what you have. There's a lot of lab sources, and here are just some typical ones. We have a centre at Manchester, there's a centre at Southampton, and then there's a few spattered around, 1 or 2 in almost every university of these lab sources. They're now like an SEM. They're 300,000 to £500,000, and they can go through from resolutions of around, if you're willing to pay 2 million, around 50 nanometers, up to, if you pay 50,000, around 10 micron resolution. But it's like any optical imaging perspective, your resolution is proportional to your field of view. It's really about a 2,000th of your field of view. So if you want to look through a rock that's a meter in size, you're just going to get something which is a half millimeter in resolution. So you often have to scale down. And they go through a whole bunch of systems. There's the inexpensive tabletop one, and if you happen to have £1 billion lying around, you can build one on the top of a mountain in Grenoble, or you can even come to Diamond, which was about 400 million. We're sitting there at Diamond, but really most of you are interested in things happening in other places of the world. Since you're geologists, we work a lot with Rio Tinto, and one of the oldest copper mines and highest yielding is just outside of Salt Lake City, called Kennecott. It's managed to yield copper for over 100 years, but they've mined out almost everything that's more than 2% copper. I don't know if you know, but it's about 8% of the world's energy is used to just grind the rock. How much does the UK use in terms of energy? Anyone know? It's about 3%. So if we can save 40% efficiency on this, we save more CO2 emissions the entire UK puts out. So what we have to do is stop grinding the rock and instead chemically treat. Especially as you go down, the energy to grind the rock is not cost effective or energy effective. So they're trying for leaching. Leaching's a lot like a lot of radioactive waste effluent. It goes out into the rock through different sizes of fragments. No one had really looked inside. So what we did is we extracted out a bunch of the rock, took it out of a leaching, and then simulated it in the lab. So we can go through and we can have the liquid permeate through, and using X-rays in a small column about this size, we can in real time look at where the liquid's going. If you have slow movement, which you probably have in most of your cases, you can track that. Using neutrons, because of the hydrogen having a high attenuation, we can combine deuterated and non-deuterated water and track where the water is. And what that's allowed us to do is compare that to models. So this is actually modeling that we're doing. And compare what's happening here to what's happening in the modeling to see that actually a lot of these effects are completely spurious in the model due to incorrect boundary conditions. So we can start seeing inside at the liquid flow. Well, the other thing that's happening in leaching is you want to get rid of the metal sulfides, extract basically go through, extract it, and convert it back to the metal. So no one had ever looked at what's happening inside. These are all the metal sulfides inside of a number of fragments in rock in a leaching column, just isolating this little bit. And they're colored by size. So the red are the smallest, the blue are the largest. This is a huge chunk of metal sulfide. And what you'd expect is that all of those, as we're leaching over a period of almost a year, to dissolve at about the same rate. These are completely picked at random, and what you see is a range in motion of leaching that spans a huge variation. Any of the processes you're looking at in terms of environmental radiation waste is going to have the same range of statistics, and it's huge. This lets you actually look inside and see it, that even in some of these cases, this large one's actually quite slow. You have a piece right on the surface of the rock which hasn't reacted, so it's passivated. So we now need to go over and look at that with speciation to see why this piece hasn't actually gone and leached at all. And it's probably a passivation of the surface. So it lets it actually quantify it and look inside and see some of these reactions and start understanding them. So hopefully that's sort of shown you an application. Looks great. it only works sometimes. There's lots of cases where it doesn't. So let's go back to some of the history and the theory and see when it might work for you, when it won't. Well, a lot of people know radiation theory. I've seen the original picture of the hand with the ring on it, which was in the 1860s. But it was actually in the 1917 that radon mathematically proved that you can take a series of projections. So if you take radiographs as I'm turning, that you can do an inverse transform in Fourier space and reconstruct the 3D image by taking a series of projections. The first synchrotron was actually built just post-war. Then they were combined. They were actually combined about 10 miles from here. So medical CT was invented at a lab about 10 miles from the current location here by Hounsfield, and that was turned into computer axial tomography. It was then refined in QMUL into something called microtomography, where they looked along a single line for dental applications. But it's dental applications that are identical to a lot of geological, is mineralization and looking at mineral speciation in 3D at very high resolution. And that's just grown and spiraled. It spiraled so much that now at Diamond, you can do tomography on I-12, the Diamond Manchester beamline, B16, B24, I-18, and soon I-14, which will, that's actually supposed to be ready. So I wonder where I got this from. That's supposed to, yeah. Well, actually, it's supposed to be ready for occupation for the EMs next summer, end of next summer. A beamline is supposed to be in 17. I guess that's probably when, oh, I know what it was. Yeah, the nano is later, is 18. So the number's actually right. So what happens is, in terms of a lab source, a synchrotron has a parallel beam. Hopefully you've learned some of that. In a lab source, you have a diverging beam. And you simply magnify. On a synchrotron, you magnify by optics later. In a lab source, you simply use a shadowgram. The closer I get to this light, the larger my hand gets. You can see it shrinking. And it's the ratio of these distances. So that tells you the sort of size you can get is how close you can get the sample to the point. And of course, when you have the sample inside of a radioactive containment, you can probably only get it within a few tens of millimeters. And you also have to know that this is an electron beam hitting a target, so you also have to have something that's non-magnetic if you're coming really close. So if you want high magnification, you bring it close to here. Low magnification, bring it close to your detector. Relatively simple, continuously variable magnification, which is great, which you don't get as a synchrotron. I just wanted to show this in terms of X-ray energies. There's a whole range of electromagnetic, and Diamond produces everything from here up to, well, produces and uses up to about here, up to about 150 keV. It does, some of the X-rays will be higher energy, but if you're looking at crystallography, mammography, medical CT, there are very narrow ranges in each one. Why? The reason is, if the energy is too low, and I'm trying to get an image of the wall, it wouldn't penetrate. I'm going to get a black image on the outside. If the energy is too high, I'm going to get an image like looking out of the glass behind you, where I see nothing of the glass, so I can't resolve it. So you have to have something where your transmission ratio, or the amount transmitted, should be on the order of about 20% of the X-rays are transmitted to about 80%. So what you have to do is pick an energy that's somewhere in between that. So too high in energy, the object seems transparent, and you have too high signal-to-noise ratio. Too low in energy, and again, you have the same thing, not enough X-rays coming through, too high signal-to-noise ratio. As it's transmitting, what's happening is it's interacting and scattering. The X-rays or the neutrons are scattering, and a fraction of them, very simply on an equation, which fortunately is relatively linear in going through an attenuation, there's an interaction where a certain number are scattered, and you get Beer's law, which just tells you as you're integrating across how much you've lost. Let's actually look at some materials that you might be interested in. Can I just ask, what sort of things might you be looking at? One or two examples. Are you looking?
So soil rock cores.
Okay, so if we start looking from quartz, which is there, it's the soil or rock quarry, you're going to, sorry, I should say zirconia. You're going to go through and have a number of different elements sitting in your rock. Because of the energy of the electrons, basically X-ray attenuation goes with the electron density. Electron density is equal linearly to density. So if you double the density of material, it has twice as many electrons. If you go up an atomic number, it goes up with about the square of the atomic number. So if you go from an atomic number of 10 to an atomic number of 20, you've actually gone up by the square of that difference. So if we look at things in terms of how much penetration depth can we get through, and we take something like 40 keV, which is perfect if you have a sample, which you probably want of soil, something about this size to this size. It's just brilliant. It goes through anything in that range. You'll get good resolution. If you've got some zirconia in there, or you've got either an iron oxide or something relatively high on the atomic number inside of it, or you've got uranium in there in high concentration, the addition of density will just be linear, but the attenuation will go up. You can now only go through a maximum of about 10 millimeters at that same energy. You also have these edges, which are the electron orbital interaction. So rather than the cloud of electrons, it's coming up to an energy at a K edge or an L edge. The nice thing here is we can scan above and below that, and you'll get very different attenuation. So you can tell not speciation, but motion of your elements, which is very useful, with much higher resolution if we scan above and below an edge. That's great if the edge is in the range where you get penetration. In most cases, the edge is down here, where if we're now down at 10 keV, I'm going through a couple of millimeters max of your soil, which isn't enough for statistics. So you need to look at this and really think, what are you doing, and plan your experiment. The other thing you need to think about is time. If you're looking at a fast process, you need to integrate up these projections as you're doing it. And it's very simple that the resolution goes up with 1 over the square root of the number of projections. And so as I go through and add at a degree and angle, so I've gone from 45 to 90 projections, you can now start seeing something being resolved. And as I go through, I can now see what my original phantom or shape is within it. So you need to integrate sufficient projections, and there's always a trade-off of signal to noise. The trade-off's quite simple. It ends up to just be pi over 2 times the pixel width. Pixel width being the pixel width of your camera, usually 1,000 to 2,000. So if you have 1,000 pixels, you need to go by pi over 2,000 number of projections to get an optimal, or something on the order of 1,500 projections. 6,000 if you happen to have a nice expensive 4,000 pixel detector. What do you get after all that if you're looking at something like a soil? So here's a nice example where I've got a bit of zircon, a bit of apatite, a bit of feldspar, a bit of olivine, some oxides of a metal oxide, and you can see a range of attenuation, which comes back to that Beer's law calculation. What we can now do is threshold this and isolate out individual elements. So we can take that and threshold it, and then we can extract out data. So this is, unfortunately, a bioglass. It's not a geological one. I couldn't find one last night. It's pores and connects, but it's very similar to what you want to do. You want to look at flow through this and see where things are going, how they're reacting. This is actually, the body deposits out a carbonated hydroxyapatite. So this was tracking the carbonate forming in different locations. At the same time, it erodes out some of the matrix. By thresholding it, we can now put numbers on things, which is what you want to do. You want to look at the interconnects to see the flow through it. Look at the size of the pores, how they change. Are you layering out and depositing locally? Are you transporting a long distance? What's happening in your mechanisms? We can take all of that and quantify and pull out each and every one of these features and put numbers on it. And what we can then do is take all of this mathematics and go through and plot your distributions and your change in distributions with time. So we can set up a reaction and track it in time and quantify it, not just get qualitative results. Well, why is that useful? Well, let's look at something that is nice and topical, fracking. I'm hoping to do the first fracking in Oxfordshire here at Diamond in a couple of months. So we will have some fracking in Oxfordshire on the beamline end, and hopefully once IMAT, the neutron source, is done. And what we really want to do is see inside of a shale what's happening. Now, if this was a classical source of petroleum, you'd have 100-micron gaps in here in easy flow of the oil or the natural gas. You really see nothing at the micron scale in a shale. There's absolutely nothing there. We zoom in, and amazingly, even as we come down to 30 microns, we still don't see, we see something that looks fully dense. So we started zooming in even further. And we zoomed all the way down, and we now flipped to nanotomography in something called 3-view, which is an automated serial sectioning inside of an SEM. And we now started looking at the connected porosity. And everyone had been looking at micrographs, 2D micrographs of porosity in shales. And they could see pores, and they thought, well, it's connected. We did it in 3D, it's not connected. None of the pores in a traditional sense, there's no connectivity of porosity in a shale on a conventional sense. Because the organic matter that's in there, which is the source of the oil and the gas, is actually in every single gap and blocking off in between the pores. So how does the gas come out when you frack it? Well, the gas now goes through the cracks you're opening, but as soon as you go into the shale, and a fracking explosion will crack up an area about the size of this room, it still has to get from a crack which is here through solid shale this distance. How does it do it? Well, that's when we go over to the neutron source and do sands and show that in the organic there's porosity, but the porosity is on the scale of nanometers. And so your gas is now permeating through nanometers, and that's why when you frack even in a room this size, in a conventional source you'd have drained all the oil and gas in minutes. If it's oil, in days. In a shale, it takes a year. And it's those sort of insights that you can use Diamond to now start and say, why, how? Where's the water going that we're putting down there? Because the water, in many of these shale mines, 80% of the water goes out and is lost. That's an awful lot. I mean, it's fine if it's up where I come from, which is Manchester, and there's lots of water and too much rain. But if you're going, and anyone know where the largest shale reserves are in the world? No guesses? Okay, it's in the desert in the west of China with no water, almost no water, and a country who are just going to take it out, right, in an already water-deprived area because they need the energy as well as the water. And so we need to think of new ways to be efficient and track where it's going, the exact same as you are in radiation waste and how it permeates out through a shale, not just through something. And I'll bet you a shale would probably be darn good for radiation storage. So what we did is go through all these scales, and at the finest scale show that, and so this is 3-dimensional, that all of this space is filled with organic and that there is no continuous porosity. The benefit there is you now have a 3D shape that you can stick straight into a flow model. So we did the scan. It was done 2 years ago. I think it was December 20th, and we finished all the computations, the reconstructions on the 21st to send off. So once you have a geometry and you know the physics, to generate out these flow models, because you have all your geometry, is actually incredibly simple. And there's simple tools. We have our own open source codes that you can use, or you can also pay lots of money as well for some nice codes too. We then looked, and we have environmental cells, and so do Diamond and so do ISIS, so that you can frack, or in this case this is a maturation or an accelerated maturation of the shale, at how these cracks open. Because you've got a time sequence, you can do a technique which the US military developed, which is tracked missile silos, digital image correlation. People know what digital image, yeah. So basically it's saying that if I look at registration when I minimize the two, one over the other, and what that tensor is moving from there to there. That's digital image correlation. You can do the same thing in 3D and get digital volume correlation. It's just 9 degrees of freedom instead of 3. And you can map all your strains. You can also map all your flows. So you can actually get all the experimental strains to now compare to your model or your flows out of that, so long as there's a texture. There has to be some sort of texturing to register that this. If it's a blank sheet and everything has equal homogeneous attenuation, but if you're looking in soils, how much of it's homogeneous? Very little. So you've got lots of texture in a soil. So this works, and you can then look at how the shale maturates, opens up, and provides pockets but not connected. And this unfortunately, well, that's pretty naughty. He's put it the wrong way. The bedding plane he's done this way. I was wondering why it's cracking that way. So it should have actually been drawn that way. It cracks in the bedding plane as you'd expect from the original sedimentation. So what can we gain? Well, it lets us answer a lot of questions. Hopefully I've shown you by doing this multi-scale imaging and correlating it. I didn't really show that much correlation with spectroscopy, but it's critical. Let's answer that the flow in the organic, well, the flow in pores is not easy. There's no connected porosity in most of the shales that we've looked at so far for the different basins. And that's very, very different than a conventional play. This is a conventional play. The scale of the flow channels is 100 microns. And we zoom in, and here's a shale. So a shale blown from there to here, there's no connected porosity. We can zoom now, it's fallen to the back, from an area of that, and come up. We've got some pores. The pores are the dark black. Let's put them in 3D, and in 3D they're the red. They're not connected. So our transport now, if you wanted to get here as a gas, and the distance to crack in a fracking is about the distance from here to New York. As a gas, you'd have to be walking in and out of a door that size 1 million times to get to that crack surface. So it tells you your transport properties are darn slow. And so what we need to do is decide how to open those up or make it effective and go through and do it. So it's given us a lot of insight into that. And it also gives us models where we can model now. And instead of modeling as open flow, we now model as a diffusivity through this organic. Fortunately, people made the measurements about 50 years ago on diffusivity because they thought they could accelerate the maturation of these source rocks, which are also our shale sources. Plug it up a scale. And so what we're doing now is going upscale to nano-CT, bring it up to the scale, and then put it into basin models, which is what do you want to do to think, if I have a leak, where's my radioactive material going? And be able to multi-scale model it to say, over an entire basin, is it going to get close to any water transport source? So with that, I just want to finish and just say, hopefully I've given some ideas of how you might use this, all the way from looking at leaching in a leaching column, through to looking at transport on a multi-level scale. But you can get the input for your models at each of these scales, and you can validate them as well by actually doing measurements. And you can go through and pass a lot of that back. I didn't cover it, so I removed that. There's also ways of looking at the speciation just from the attenuation contrast, and that's now being used. We're analyzing samples from volcanic eruptions to tell whether they're going to be explosive eruption or not by the olivine concentration. So you can get, if the speciation changes the attenuation or K-edge, you can get some of that. With that, just to say the work is that of a whole big group. We're really happy to collaborate with people. We're based here, but also in Manchester. But we work with people. We work with 35 different universities and 80 different industries around the world. So we're very happy to have a chat. And so are all the people at Diamond and ISIS. I've just put a few references. There's some really great public domain software out there, some great tutorials as well, and projects that both we've written and other ones that are actually better from some of the other groups. So you can teach yourself some of this in terms of the reconstruction and techniques, but we're very open to interaction. Questions, please.
Do we have any questions from Peter?
It's a good chance if you have a problem, you want to know whether it works or not, to speak up.
I have a question about access. So I certainly know within the low-rise program that's funded through NERC, through this rate scheme, there's a good chance that some of us might want to come and do some tomography as we go through the program. So how would we gain access?
So the Diamond is by application. So this is the standard route. And the center I run, we also have 80 days of time, which we can use on specific. We keep a fraction back. We keep 20% back for feasibility. So we can do a quick test and help you then go through. In terms of the laboratory source, and you should try in the lab source first, everything we run is a small facility, if you're familiar with small facility. It's a research council mode where you don't pay for the capital, you just pay for the running costs. So typical sort of charges are a couple of £100 a day. The reality is we help everyone, but if you can pay, we'll take the money and you get priority. If you can't pay, we'll help you, but the people who are paying go first. That's it. And the ideal, we always ask, is that if you're part of a larger group, one person comes, gets trained, because a big amount of that cost is the people. So we train it. And so Diamond and the collaboration that we run courses at the beginning of each AP, so actually 4 times a year, on how to analyze all of this. And the run here, they send out, the user office send out the announcement to anyone who's registered for an experiment on any of those beamlines, or if you just drop me an email, I'll get you put on the list. The next one's December 3rd and 4th course. I think there's still a couple of spaces. No one interested in using it? No? Okay.
Some people want to come and visit later on, so I guess they can ask questions then. Thank you very much.
Okay.
Okay, guys, so we had penciled in the timetable kind of a general question and answer session now, but I think we've had a lot of questions as the talks have went on, and we certainly have time to ask questions as we're going to do tours of the facilities. So based upon the information given earlier, there was a kind of broad interest in some people going to ISIS and some people going to see the Central Laser Facility, and then coming back here and then touring both Diamonds and then going across the Peters area. So I think what we'll do now is we'll just break off into 2 groups. So the people that want to go to ISIS, please congregate around Steve, and the people that want to go to Central Laser Facilities, Andy's at the back. And then if we could have those guys back here for about 2:45. Your text is on 10 to. Well, how long do you think you need?
If you walk past
But you want to see Diamond as well, right?
It's an individual program, 2:30 to 4, isn't it? So as long as they're back by 5,